Welcome to Efiwe, excellence without stress.
Hi guys, we are back again and it's me, Miss Stella, your favorite physics tutor, and today on our journey into excelling without stress, we're going to another very interesting topic in physics, which is AC circuit. So simple AC circuits. In our previous classes, we've explained direct current, which is DC circuit, DC direct current. So we've explained the direct current, and you know that that's the kind of current that we get from our batteries. And I explained to you that that one moves in a straight line. It moves in one direction. It moves in a single direction. It doesn't alternate or anything, but the alternating current moves in an alternating manner. It goes forward and backward, and that's why we cannot even actually say, okay, this part is the positive part of the circuit or this part is the negative part. You know, when we connect and when we have a DC circuit, we can actually detect the positive part and the negative part, because the part of a DC current is one. It moves just from the positive to the negative. But for the simple AC circuit, the positive changes to the negative and the negative changes to the positive. And this is what we can see here now. This is like an alternating current. This is the sign of an alternating current. You can see this is the current, this is the load, and this is what we call an alternating current. Alternating current circuit. AC circuits are circuits through which an alternating current flows. Such circuits are used extensively in power transmissions, radio, telecommunication, and medicine. Alternating currents are produced by time-dependent alternating voltage given by the relation E is equals to E naught sine WT, and this is because they move in a sinusoidal manner, and that's why we have this relation. We can remember this when we're doing progressive wave to add a relation that looks like this, where E naught for the progressive wave, it add A amplitude as the E naught, which was representing the magnitude of the amplitude, and amplitude is the highest energy. So for this alternating current, E is equals to E naught sine WT. Anytime you say E naught, it's talking about the peak energy. Much of what we learned about DC circuit also apply to AC circuits. Yes, because also here we're going to talk about resistance, the opposition to the flow of current, but the names might be different. Resistance in AC circuits, we call it reactance because it's the opposition to the flow of current. You're going to have current too, you're going to have voltages. So the effect on such voltages on resistors, capacitors, inductors will be discussed. In this case, we're going to the effect of alternating currents on resistors, on capacitors, and inductors will be discussed. Nomenclature in AC circuits. An alternating current is one that varies sinusoidally or periodically in such a way as to reverse its direction periodically. It reverses its direction, and that was what I explained in the previous slide. The commonest form of such an AC can be represented by this. So the current is represented by I naught sine 2 pi ft, while I naught is telling us the peak current. Let me show you where the peak current is. This point, it's just like when we were relating to waves. The peak point here, which is called the amplitude, for an alternating current, this point is called the peak current. That is the maximum current. So an alternating current is one that varies sinusoidally or periodically in such a way as to reverse its direction periodically, and this is the commonest form. So I naught sine 2 pi ft. Don't forget that 2 pi ft is the same thing as omega, which is our angular frequency. So this relation can be like this. So if you are given an equation 2, just like we did when we're studying waves, you can easily be able to detect, oh, this is I, and you can put this formula into the equation you are given. So I is called the instantaneous current, that is current at a particular time, at an instant time. So it's called the instantaneous current at a time t. I naught is the maximum or peak value of the current or its amplitude. Yes, F is the frequency, and omega 2 pi f is the angular velocity. Wt, because of the Wt here, is called the phase angle of the current, the phase angle of the flowing current. Alternating current voltage is also represented the same way. You know, we are talking about two things. We have the current, now we're talking about the voltage. Don't forget the Ohm's law, V is equals to IR. So now also for alternating current, the voltage can be represented the same way. V naught sine 2 pi ft, V naught sine omega t, where omega is what? 2 pi ft. Here, V naught are instantaneous or peak or maximum values of the voltage. So V naught is the maximum voltage, while V is the instantaneous voltage. So let's check this example. If an AC voltage is represented by the relation V is equals to 4 sine 900 pi t, the peak voltage automatically, just as I've said, let's go to our board. Sorry. Let's go to our board to check what we are trying to say. So look at it now. We're given the relation V is equals to 4 sine 900 pi t. V is equals to, we're giving V, right, is equals to 4 sine 400 pi t. And don't forget what we said. V is equals to V naught sine what? 2 pi ft. Or V is equals to, V naught sine what? Let me just delete this. Control delete. So we have that. They said V is equals to 4 sine 900 pi t. Let's check if that's what we were giving. If that's what we were giving in our 4, okay, is equals to 4 sine 900 pi t. 4 sine 900 pi t. And don't forget your V is equals to V naught sine WT. So V is equals to V naught sine, you can call it 2 pi ft or WT. So now, if you are asked for your peak voltage, you don't need to solve anything. You just relate it. So peak voltage is what? Is equals to 4 volts automatically. Then if they ask you for your frequency, you know automatically you will relate this to this, as if you are going to say 900 pi t is equals to what? 2 pi ft. And you know pi t, we cancel what? Pi t. So f, 2f is equals to what? 900. And f is going to be equals to 900 divided by 2. So f is equals to 450 what? Hertz. That's just what we are trying to say here. With the equation, you are able to get, so we have it as 450 hertz. So what did they ask again? And the peak voltage, we have it. Then W is equals to 2 pi F is equals to what? 900 pi. And that is that. That's what we are trying to understand. Once you know this formula and you are given an equation, you'll be able to detect and get anything from it. Peak and RMS values of AC. So RMS is called root mean square. So we want to check the peak value and the RMS value of AC circuit. So look at it now. This diagram has showed us the upper point. Look at it now. It's called the peak value. It's called the what? The peak value. And half of it is called the average value. Then we have the root mean square value. The root mean square value, which is called the RMS value of the current. And this is it. You can see the sinusoidal move. From here to here is called the pi over 2. The whole one is called pi and full one is called 2 pi. I'm sure we understand that from our study in waves. Just as if I said, I told you that a wavelength is what? Is the distance between two successive troughs or two successive crests. So if I close this one and close this one, it's as if I have a whole wave. If I close this one at this point and I close this one at this point, as if I'm having a whole wave, and that is what? Pi. That's why you have it as 2 pi. This place is pi over 2. This place is pi. Then this place is what? 2 pi. Is 2 pi. So an alternating current varies sinusoidally as shown below, which is in a sine wave form. The amplitude, this is it, or peak value of the current I naught is the maximum numerical value of the current. And this is it on this graph. You should be able to label the graph. Half of this is pi over 2. The full one is pi. Then 2 of this is 2 pi. You should be able to get that. And that's why we have it as 2 pi ft. 2 pi ft. This is sinusoidal AC of current wave. The root mean square value of the current is the effective value of the current. It's the effective value. So root mean square current is that steady current which will develop the same quantity of it in the same time, in the same resistance. It doesn't change. So root mean square current is that steady current which will develop the same quantity of it in the same time and with the same resistance. Then root mean square value for the current is given by IRMS is equals to what? The peak current divided by 2. Don't forget that this root mean square that doesn't change is equals to the peak value. Remember where the peak is. It's just this one divided by what? 2. Divided by 2. So don't forget that. Divided by root 2. IRMS is equals to I naught over root 2 divided by root 2. And this is the value of root 2, 0.7071 meter. So let's go back to the next slide. So it's equals to what? I naught divided by what? Root 2. I naught divided by root 2. So the RMS value of the current, IRMS, is given by I naught divided by root 2. Then I naught can now be what? IRMS what? times what? Times root 2. IRMS times root 2. That is what the this thing, the I naught, the peak current 2 can now be given as what? IRMS times this, which is root 2. The moving iron and the volt wire meters measure the average value of the square of the current, called the mean square current. They are, however, calibrated in such a way as to indicate the RMS current directly. Thus, most AC meters reach the effective or RMS value. The average value of an AC voltage or current is zero. Resistance in an AC circuit, just the same way we have resistance in a DC circuit, we have resistance in an AC circuit. At any instant, the current through the resistor R is I and the voltage across it is V. So you remember from Ohm's law, V is equals to IR. You guys remember, right? Yeah, I'm sure you do. So V is equals to IR. Thus, the current is given by I is equals to V over R. You know, we are talking about alternating current. So majorly our focus in this class will be about the current, the alternating current. So thus the current is given by I is equals to V over R. And don't forget, we know what our V is. Our V is our instantaneous voltage. So if we put V is equals to this, then the current is also going to be given as I is equals to V naught sine omega t R. I'm sure we understand that. Let's go to our board to quickly write something. We've agreed that we said that our V is equals to what? IR. So if we are looking for our I is equals to V over R, right? And don't forget, we've already agreed that V is equals to V naught sine omega t, where omega t is the phase angle. So that's, you can also write this as what? V naught sine what? Omega t over R. So this is the relationship between I and this. So I is equals to V over R, and it can also be equals to V naught sine WC, where V naught is the peak voltage and R is the resistance. R is the resistance. So look at it. This is what I was trying to say. Sorry that the board did not show. It said V is equals to IR, then I is equals to V over R. Don't forget your V is V naught sine WT. V naught sine WT over R. And that's why we've gotten this relationship. So the voltmeter and ammeter connected in the circuit will read the RMS value of the voltage and current. You know that the ammeter measures current and the voltmeter measures what? The voltage. It reads the value of the current, and this one reads the value of the voltage. Yes, we can also write that IRMS is equals to VRMS over R. Don't forget that your IRMS, because I is equals to V over R, IRMS too can be VRMS over R. The voltage and current are said to be in phase or in step with each other. This means that both of them attain their maximum zero and minimum values at the same instant of time. That is when you say that they are in phase. So let's check this question. Find the root mean square value of the sinusoidal voltage with peak value 480 volts. With peak value 480 volts. Solution. So now we can write our equation first. We already know that V naught is equals to what? Root 2 multiplied by what? VRMS. Yes, we do not forget that, because we have that. VRMS is equals to, let's go to our board. We know that VRMS is equals to what? V naught over what? Over root 2. So our V naught now can also be equals to what? VRMS root 2. So if you are asked to look for your peak voltage and you have your VRMS, you are good to go. So that's what we have. So V naught is equals to VRMS multiplied by root 2, and you will get your peak voltage. So the question is, find the root mean square value of the sinusoidal voltage with peak value 480. Okay, in this question now, we were given our peak value, then we're asked to look for our VRMS. So we're given our peak value as 480. We're given peak value, that's V naught, don't forget that, to be 480. And we're asked to look for our VRMS. So VRMS is just V naught divided by root 2. And that's going to be equals to what? 480 divided by what? Root 2 divided by root 2, and we are going to get our answer divided by root 2. So that's how we got that. So your V naught is this. So doing the right calculation, you're going to have 480 divided by 1.414, which is equals to what? 339.46, and that is that about getting the peak voltage. Capacitance in AC circuit, don't forget capacitance is the ability of a capacitor to store charges. So now we want to talk about capacitance in AC circuits. When capacitors are connected across a direct current DC supply voltage, they become charged to the value of the applied voltage. You remember that we said they can store charges because of the dielectrics between them, which will not allow it to flow. Currents flow in a straight line in one path, but because of the dielectrics, that's why capacitors are able to do what? To store charge. So capacitance is that ability, is the energy, is the smart way capacitors are able to store charges. So when capacitors are connected across a direct current, DC supply voltage, they become charged to the value of the applied voltage, acting like temporary storage device and maintain or hold this charge indefinitely as long as the supply voltage is present. During this charging process, a charging current I will flow into the capacitor, opposing any changes to the voltage at a rate that is equal to the rate of change of the electrical charge on the plate. Thus, charging current can be defined as I is equal to the capacitance dV dt. So once the capacitor is fully charged, the capacitor blocks the flow of any more electrons onto its plate as they have become saturated. This is like charging of the capacitor. However, if we apply an alternating or AC current, the capacitor will alternately change and discharge at a rate determined by the frequency of the supply. So it is continuous. It's not like the AC circuit that is just in one direction. Then the capacitance in AC circuit varies with frequency as the capacitors is being constantly charged and discharged. It's constantly charged and discharged. We know that the flow of electrons through the capacitor is directly proportional to the rate of change of the voltage across the plate. Then we can see the capacitors in AC circuits like to pass current when the voltage across its plate is constantly changing with respect to time, such as in AC signals. But it does not like to pass current when the applied voltage is of a constant value, such as in DC signals. It doesn't want constant. It wants a continuous, a changing. That's for the AC circuit. Note, in a capacitor, the current I is said to lead the voltage by 90 degrees. So the current runs, it's leading it. Like if you are having you're having the, what's it called? I and V running. If you have I and V on this thing, I is going to be running faster than what? So that is what they mean by I and V. So one is faster than the other. So I is. So in a capacitor, the current I is said to lead the voltage by 90 degrees or pi over 2 radians, and the voltage is said to lag the current. And the voltage is said to lag. Don't worry, you would understand so well during this class. So I is said to lead the voltage by 90 degrees or pi over 2. Or radians, and the voltage is said to lag the current. So we can do that. We already know what pi over 2 is. So look at it now. So we have it like this. We have the voltage, we have the current. We know half of this is pi. So as both of them are moving, so which one is leading? This is I. This is going to be the position of I. Is leading by pi over 2. Then this is the position of V. I is the one that is leading by pi over 2 or 90 degrees. Pi over 2, because we take pi in when we are talking about this sinusoidal wave. Pi is 180. So it's leading it by 90 degrees or what? Or pi over 2. By 90 degrees or pi over 2. So in a capacitor, the current I is said to lead the voltage by 90 degrees or by pi over 2 radians, and the voltage is said to lag the current. And so we can continue. Capacitive reactance. I told you that we are going to be seeing the same terms, but reactance, when we talk about reactance, we're talking about opposition to the flow of current. But now we're talking about it in an AC circuit. So capacitive reactance in a purely capacitive circuit is the opposition to the current flow in AC circuits only. So when we're talking about opposition to the flow of current in AC circuits, we talk about the what? We talk about the capacitive reactance. Like resistance, reactance is also measured in ohms, but is given the symbol X to distinguish it from a purely resistive value, as reactance can also be applied to inductors as well as capacitors. It is more commonly known as capacitive reactance for capacitor in AC circuits and is given the symbol XC. So anytime we see X, reactor is just reactance, and C is telling us that the capacitive reactance. So we can actually say that capacitive reactance is resistance that vary with frequency. Capacitive reactance is resistance that varies with frequency. Resistance that varies with what? With frequency. That's our capacitive. And this is the symbol. Don't forget that. X. Anytime you just see X, try to remember reactance. X, then C is a capacitive reactance. So X is telling us that this is a reactance. Then it can be reactance what? Capacitive reactance. That is done by a capacitor. So also capacitive reactance depends on the value of the capacitor in farads as well as the frequency of the AC waveform, and the formula used to define capacitive reactance is given as this. Xc is 1 over 2 pi Fc. Don't forget 2 pi F is omega C. So don't forget that. If you want to look for the resistance, the capacitive reactance, we call it, this is 1 over 2 pi Fc or 1 over Wc, 1 over Wc, where F is in hertz. Frequency is in hertz and C is in farads. Don't forget that 2 pi F can also be expressed collectively as the Greek letter omega to denote an angular frequency. From the capacitive reactance formula above, it can be seen that if either of the frequency or capacitance were to be increased, the overall capacitive reactance will decrease. Why? Let's go back to explain. I already told you, this is as if I'm saying the capacitive reactance is inversely proportional to the what? To 2 pi Fc. So capacitive reactance is inversely proportional to what? F. It's inversely proportional to F, which is what? The frequency, and also to C. That if you have seen anything that has an inverse 1 over, it means that thing on top, as it's increasing, the one below will be what? Reducing. But if they are on the same path, then they are what? Proportional to each other. So from the capacitive reactance formula above, it can be seen that if either the frequency or capacitance were to be increased, the overall capacitive reactance will decrease. As the frequency approaches infinity, the capacitor's reactance will reduce to 0. So if the frequency is increasing, the capacitors will start their reactance, which is their resistance, would what? Reduce to 0, acting like a perfect conductor. You know that reactance is in opposition to the flow of current, but now we're talking about in an AC circuit. In an AC circuit. So what are we saying now? If F increases to its maximum value, like to infinity, then what is happening? The capacitance will reduce totally. The capacitive reactance will reduce totally, and that the capacitor reactance will increase up to infinity, acting like a very large. No, as the frequency approaches infinity, the capacitor's reactance will reduce to 0, acting like a perfect conductor. However, as the frequency approaches 0 or DC, the capacitor reactance will increase up to infinity, acting like a very large resistance. This means that capacitive reactance is inversely proportional to the frequency for any given value of capacitance, and that's so easy to know. We already know that we already know that Xc is equals to what? 1 over 2 pi Fc. So F is inversely proportional to what? To the reactive reactance, the capacitive reactance. Then we have this now. Don't forget from your Ohm's law. Everything we're going to do, as soon as we are applying our Ohm's law, but the terms will be different. So our V, instantaneous voltage, is the same thing as Ixc. Ixc is now acting like what? R. We will call that V is equals to IR. V is equals to R. Let's go to our board to check that. We know that V from Ohm's law, V is equals to IR. So when we are now talking about in an AC circuit, now what are we going to be saying? V is equals to what? Xc. This is the capacitive reactance for a capacitor. So this is the capacitive reactance. So when we have for the inductor too, it's going to be V is equals to IXL. IXL showing us that that's for an inductor. So when an AC voltage of frequency F is applied to a capacitance, then V is equals to what? Ixc. V is equals to Ix. Let's proceed. This is an example. At frequency 50 Hz, A capacitor 5 microfarad is connected to a circuit 230 volt supply. Find the capacitive reactance. Take pi to be 3.142. So what were we giving? We're giving our frequency. We're giving the capacitor. Yeah, and this is like 5 times 10 raised power minus 6 farad, right? So what were we asked to look for? The capacitive reactance. Xc is equals to what? Don't forget, our Xc, capacitive reactance, is equals to 1 over 2 pi F, then capital C. This is the capacitor. That's the capacitance. That's the capacitance, the total capacitance. So let's go. Capacitance is the ability of a capacitor. Why the capacitor is the what? Is the device that does what a capacitor can do. So at frequency 50 Hz, a capacitor of 5 microfarad is connected to a 230 volt supply. Find the capacitive what? Reactance. So we have it that Xc is equals to 1 over 2 pi Fc. We can get it, Abi, right? Supposing we were given our current and we're given our volts, you can get it also. It'll just be what? V. 55 microfarads. So yeah, now what are we going to get? So we are going to have it as Xc is equals to 1 over 2 pi multiplied by our F, then multiplied by our C. What was our F? What F were we giving? Our F was 50. Our F was 50. Then our what? C was what? Our C was 5 times 10 raised power minus 6. So our C was 5 times 10 raised power minus 6. So we have our Xc. So putting it into our calculator and solving it, we're going to get the capacitive reactance to be 636.54 ohms. Is a resistance, and the unit is ohms. The unit is ohms. So inductance, the former one was a capacitor in an AC circuit. Now inductance in an AC circuit. Why capacitance is known to store volt energy in the form of electric field, inductance is known to store energy in form of magnetic field. That's just the difference. This stores energy in form of magnetic field, while the capacitor store energy in form of what? Electric field. It is not to oppose a change in electric current flowing through it. It is measured in Henry. It's measured in Henry. So in an inductor, we already said that the current is said to lag the voltage. So this is for an inductor. Remember we did the one for a capacitor. What happened? The current was leading. But in an inductor, current is one that is lagging. Why the voltage is what? It said current is said to lag the voltage by 90 degrees, and voltage is said to lead the current. So how will that look like? If you are going to do this just the same way I did this, in this other one, this place will be what? Will be the current. Why this one will be the voltage? Because the voltage will be leading. The voltage will be the one what? Leading. Voltage will be the one leading. So that is it. That's what about that. So inductive reactance is just like the opposition. So this one is XL is equals to 2 pi FL. Let's go and write that on our board. That one we have, we said capacitive. The one in a capacitor was what? 1 over 2 pi F, then C, capital C, then XL. The inductive reactance is 2 pi F, then L, 2 pi FL. 2 pi FL. So don't forget that. This one is now telling us that the capacitive reactance is what? Directly proportional to the frequency in this one. But in capacitive reactance, it is inversely proportional to the what? To the frequency. So as the frequency is increasing here, this one is reducing. And as this one is increasing here, this one also is increasing. That's just the difference. Capacitive reactance, inductive reactance. Inductive reactance. So let's go back to our slides to continue. That's the inductive reactance. So and we have it as the same way we had that one. It also was V is equals to IXL. V is equals to IXL. Where XL is your what? Is your inductive reactance. Is your inductive reactance. Let's proceed. So series circuits containing resistance, inductance, and capacitance. So now we're not talking about a series circuit that has resistance, that has inductance and capacitance. So if an alternating voltage V0 sin 2 pi F is put across the circuit, it is then observed that a steady current given by I equals to I naught sine 2 pi ft, we flow along the circuit. It can be shown that the maximum or peak value of the current is given by this. I naught is equals to V naught over, in this case we have what? We have resistance, we have inductance, and we have the what? Capacitance. So what are these? These three are resistance. Recall that. Recall that we have that our V is equals to IR, right? So if I'm talking about, what's it called? I now. I is equals to V over R. So we're not talking about the peak voltage. V naught is equals, I naught. Let me delete the board so we can have it. So if we have from Ohm's law, V is equals to IR, right? So I is equals to V over R. So if I'm talking about I naught will be equals to V naught over R. So now we're talking about a circuit that has it has capacitive reactance, it has inductive reactance, and it has resistors in resistors too. So what are we going to have? So I naught will be equals to V naught divided by what? The square root of R square plus XL minus XC all squared. Okay, yeah, squared too. Sorry, forgot to put the square of that one. So that one is all squared. So we have it like this. So this is how to find the current, the peak current when it is in resistance having RLC, having the resistance, having inductor and the capacitor. Resistors, inductors, and capacitors. They are general resistance. So your I naught is also V naught over Z, because Z is called the impedance. Z is called, because all of this now, R square plus XL minus is called Z. So this is now going to be I naught is equals to V naught over Z. So this is called impedance. We are going to know what is in the next slide. It's called impedance. So, and VRMS is equals to Z as just all the relations. You can put them together. I naught is equals to V naught over Z. IRMS also is equals to VRMS over Z. Z is known as the impedance, which is the overall for everything, for capacitors, for reactants, and for everything, for resistors. So for inductance, resistors, and capacitance, Z is known as the impedance, which is the overall opposition of a mixed circuit containing a resistor, an inductor, and or a capacitor, and it is measured in ohms. Every form of resistance, either is called the reactance or impedance, is called what? Is measured in ohm. So we have our Z to be equal to this. You remember that your R is R, your XL is 2 pi FL, your XC is 1 over 2 pi FC squared. So summarizing, we have that the voltage across an RLC, VR is equals to R. You know this one is for a resistor. This is L, is equals to IXL. We telling the current multiplied by the what? Inductive reactance. Then VC is equals to I multiplied by the what? Capacitive reactance. Then V is equals to IZ. For a RLC circuit, your V is equals to all of this. Resonance in an RLC series circuit. Resonance is said to occur in an AC circuit when the maximum current is obtained from such a circuit. Simple as ABC. Resonance in an RLC circuit is said to occur when the maximum current is obtained from a circuit. So the frequency at which the resonance occurs is called the resonance frequency. That frequency in which where maximum current is obtained is called the what? The resonance frequency. And this happens only when XL is equals to XC. It happens when XL is equals to XC. So if we do this, our equation like this, recall that XL is equals to this, XC is equals to this. Putting the two of them together, let's go to our board to do that. Recall that we have that our XL is equals to 2 pi FL, right? We have our XC to be equals to 1 over 2 pi F what? FC. So if we are equating these two together, 2 pi FL is equals to what? 1 over 2 pi FC, right? So if I cross multiply, it's as if I'm saying this is equals to this. So let's continue from our slides to see what we are doing. That's what we got from it. That we are equating these two together. Don't forget, we are going to be putting, resonance frequency is when XL is equal to SC. F naught is telling us that, okay, this is the resonance frequency. So F naught now, for two of them, is equals to 1 over 2 pi LC. Because these two will cancel each other. What is left here is L and C. So, and don't forget your W is 2 pi F. So W naught is 1 over what? Square root of LC. 1 over square root of LC. 1 over square root of LC. All of this with 2 pi F naught L is equals to 1 over 2 pi F naught C. Pi F naught C. And if we do the right equivalence, we're going to have 1 over 2 pi F naught C and LC. So LC is what we have here. LC is what we have here. Since W is equals to 2 pi F, W naught is equals to 1 over what? Square root of LC. 1 over square root of LC is equals to 1 over square root of LC. So note, in a capacitor, don't forget current leads. We've already accepted this. You can see that current leads by this. If you can, what's this thing is this one. You can see the one leading and you can see the one lagging. So current leads the voltage by 90 degree or pi 2 over radians. While voltage lags the current by this. While in an inductor, current lags voltage by 90 degree and voltage leads by current. Don't forget this. All these questions can be asked. Thank you. And this is all for this class. See you in our next